Hi, everyone. So I wanted to work through a problem that I think is a little bit tricky to give you a sense for how you can solve slightly more complicated problems with capacitors. Um, so let's just get into it. So I'm taking Giancoli problem 24.8, should be in your book, and you can look it up and try it for yourself if you want before you watch this video. But I'm just going to work through my solution. So the statement of the problem, there's a 2.4 microfarad capacitor, which is charged to 880 volts, and a 4 microfarad capacitor that's charged to 560 volts. So I drew a little picture for how you might achieve this. You just connect a battery of 880 volts to this capacitor and wait for it to come to equilibrium. And similarly for the other one, connect a battery of 560 volts and wait for that to come to equilibrium. And we want to figure out two things. So after you do this charging, you disconnect the capacitors from their batteries, and the positive plates are now connected to each other, and the negative plates are connected to each other. What will be the potential difference across each capacitor and the charge on each? So that's an interesting question. So how do we do that? First, let me figure out how much charge is on each capacitor. So I can use this relationship that we have. So we have this definition for capacitance. C is defined as the ratio of charge to voltage. So if I wanted to figure out how much charge was on each capacitor, I could say the charge on the first capacitor is the capacitance times 880 volts. And I think if you do that, you get 2.11 microcoulombs. So note here, the C here is a unit, the Coulomb unit, not another capacitor, which is a little bit confusing, but those are the units we got. So in the next one, I can get the charge on the second capacitor. That's equal to the second capacitance times 560 volts. And if you do this, I think you get that Q2 is equal to 2.24 microcoulombs. Okay, or excuse me, millicoulombs, not microcoulombs. Okay, so now the problem says that we want to disconnect the capacitors from the batteries. So if we do that, the capacitors just hold their charge, because if we're disconnecting from the batteries, there's nowhere for the charge to go. So the capacitors are just storing that charge. And then we reconnect them such that the positive plate of each capacitor is attached together, and the negative plate of each capacitor is attached together. So let me just make a mark here. So let me say that in the first diagram, this would be the positive plate and this would be the negative plate, because the positive plate will be attached to the positive terminal. And similarly here like this, just to kind of keep track of where things are going. So if I take, let me scroll down a little bit. So if I take the first capacitor here, so here's the first capacitor, here's the positive plate, here's the negative plate. And then I hook it up to the other, oops, I want those to be the same size. And then I hook it up to the other capacitor, that was C1, here's C2. Then I'm hooking up the positive plate there to the negative plate there and doing it like that. So that's the circuit that I'm creating now, which is a little bit weird. So what's going to happen when I do this? Well, the voltage of these capacitors is going to change. There's no reason why 880 or 560 has to be represented here again. The physical thing that's in the system is the charge, and the charge will flow until the electric field everywhere is zero in the wires. And so like the charge here will reorganize itself. And I'm going to say that on capacitor 1, I'm going to have some new charge here. I'll call it Q1, little q1, as opposed to big Q1 from before. On this side and negative Q1 on this side. The charges on each plate will be the same in magnitude. And then on the other capacitor, I'll have some Q2 there and some negative Q2 there. And what I know for sure is that when I put these two capacitors together, there was big Q1 on the first capacitor and big Q2 on the second capacitor. That was how much total charge in magnitude I had on each wire. So like this wire has total charge of this. And all that's happening is that the charge is being redistributed because the physics has changed. And that means that whatever Q1 and Q2 are, they have to add up to the total amount of charge that was there before. The charge isn't going anywhere. It's trapped on that wire. Can't really go anywhere. Also, there's no reason why the voltage has to be constant, but what has to be true is that this wire, once I reach equilibrium, there has to be some constant voltage. I'll call that V high. And on this wire, there has to be some constant voltage. I'll call that V low. So what else is true is that if the left wire has a constant voltage and the right wire has a constant voltage, then the potential difference across each capacitor has to be the same. It's kind of like I've attached these capacitors in parallel. And when you attach capacitors in parallel or anything in parallel, the voltage difference has to be the same. So I'll call that V naught is this difference, V high minus V low. And that's just the same thing as the potential difference across each of the capacitors here. So how do we proceed from here? Well, I'm going to use this equality that I just wrote down, that the potential difference is the same for both capacitors. And I'm going to write that a different way. I'm going to use our expression for charge, capacitance, and voltage to write this down. So V1 is equal to Q1 over C1. And it's also equal to V2. And V2 is equal to Q2 over C2. So I can say Q1 over C1 is Q2 over C2. But I also know that Q1 and Q2 add up to something. So if I add up Q1 and Q2, so big Q1 and big Q2, that's 4.35 millicoulombs. So I can substitute in for, let's say, Q2 if I wanted. So this is the same thing as saying Q1 over C1 is equal to 4.35 minus Q1 over C2. I've just substituted, I've rearranged this equation, solved for Q2 and substituted it here. So all it's saying is that Q2 is equal to however much charge you have left over once you subtract Q1 from the total charge. And then this is just an equation that can be solved. So there's some algebra here. So I'm going to do some algebra. Scroll down a little bit. So bear with me. C2 Q1 equals C1 times 4.35 minus Q1. Then I want to clump all the Q1s. So C1 plus C2 times Q1 is equal to C1 times 4.35. So Q1 is C1 over C1 plus C2 times 4.35. So some ratio of the total charge, which kind of makes sense. So does this expression make sense? How much charge should Q1 have? Well, if C1 is bigger, so if the capacitance is larger, then that capacitor gets a larger proportion of the total charge, which kind of makes sense. If you have a larger capacitance, you get a larger proportion of the total charge. That makes sense. So let's do this. So C1 is 2.40 microcoulombs. I'm going to drop all the microcoulombs because I'm just taking a ratio. And then 2.4 plus 4 microcoulombs is C2 times 4.35. In 4.35, I'll keep the units there, millicoulombs. Well, I think I said coulombs for the capacitor too. It should be microfarads, excuse me. But millicoulombs for the charge. And if I do that, I get 1.63 microcoulombs. And then Q2 should just be 4.35 minus Q1. If I do that, I get 2.72 millicoulombs. Okay, so Q1 and Q2 are this. So the charge has been redistributed across the capacitors. Originally, let's see, so originally it was much closer to equal charge, but in the second case, more of the charge ended up on the larger capacitor, proportionately with the size of that capacitor. Okay, so the problem also wants the voltage. So if we want to go back and get the voltage, we can just use one of the expressions for voltage here to get it. So V naught is the same thing as V1 or V2, so I just have to calculate it once. So, oops, V naught then is equal to Q1, let's say, over C1. So that's equal to 1.63 millicoulombs over 2.40 microfarads. And if I do that, what do I get? Let me calculate that. I get about, I guess I did it, I paused the video and then calculated it in Google and wrote it down. So I get 679 volts about. So it's not even, it's in between the original two voltages, 560 and 880, although it's not the midpoint between them, which is kind of interesting. So the way to think about it was just in terms of the charge here, the charge, the physical aspect of the charge moving around until equilibrium was reached. So that's part A. So I guess I'll box that result too, equals V naught. Okay, so part B. So in part B, you take the plates, the positive plate of one capacitor and connect it to the negative plate of the other capacitor. So that would be like if I take C1, oops, if I take C1, so in B, I'm taking C1, and let's say I have the positive plate. Why do I keep drawing it like it's a battery? It's a capacitor. So positive plate there and negative plate there. And then I connect that to the other capacitor. So this one's C1, this one's C2. And I connect the negative plate of C2 here and the positive plate of C2 there. Oops. Like that. Okay, so now I'm just going to do the same thing. I'm going to define Q1 and Q2, except that now what's true is that here, the total charge there would be Q1, positive Q1 minus Q2. The total charge there would be that, and the charge would be opposite on the other side. And I'll just define, this thing has some V high again. This thing has some V low again. So the difference V naught is, I'm defining it the same way. I define Q1 here and negative Q1 here. I define Q2 here and negative Q2 here. And I'm not thinking too hard about the signs of things. You'll notice that actually the way that I've defined these charges, Q1 minus Q2 is a negative value. So Q1 was 2.11 millicoulombs. Q2 was 2.24 millicoulombs. So if I take this difference, it's actually a negative value, minus 0.13 millicoulombs. And so I should probably expect that what I called Q1 and Q2, those should probably be negative values because the total charge on that wire is negative, but that should come out in the wash. I'm not going to think too hard about it and then just worry about the signs at the end and hope that makes physical sense. So what I'm expecting here, based on the way I did things, is that Q1 and Q2 are actually negative values. And I hope that I get that in the end. So let's see. So it's the same thing here. Q1 plus Q2 is equal to big Q1 minus Q2. because the charges are just sort of reorganizing until equilibrium is reached. But also same thing, V1 equals V2 equals this difference that I've defined here, which I'll just call V naught. And so I can take the exact same approach as in the previous problem. All of the difference has already been described here. And the only real difference is sort of this thing, that instead of having an addition of charge, I'm getting a difference of charge when I do this. So I should expect that the voltages should be a lot smaller because the magnitudes of charges on these capacitors are going to be a lot smaller. So let's see what happens. So I'm going to do the same thing. So I'm going to say that V1 is Q1 over C1 is equal to V2 is equal to Q2 over C2. So working through a similar process, Q1 over C1 equals, now Q2 would be minus 0.13 minus Q1 over C2, replacing Q2 there. So if I start grouping some things, Q1, C2 times Q1 equals minus, I guess I'll do it this way, minus there minus Q1, C1. If I move the things to clump Q1, I get C1 plus C2 times Q1 is equal to minus 0.13 C1. Okay, so we can see here that we are going to get a negative value for Q1. So let's solve for that. So Q1, I'm running out of space, but that's okay. Q1 is equal to C1 over C1 plus C2, the same ratio we had before, which makes sense, times negative 0.13. So it's really the same solution we had before. If you look back up here, it's the identical solution, just with a different sort of total charge that we're working with. Above, it was the addition of the charges, and here it's the difference of the charges. So what do we get if we do that? I get negative 0.049 millicoulombs. Okay, so that's Q1. And then Q2, if we take a difference, we should get 0.081 millicoulombs, because that should add up to the negative 0.13 that we had before. And then if we wanted the voltage, we could do the same thing as previously. So let me do that. So that voltage, if I take Q1 and C1, is I get about negative 20.4 volts. Okay, so I've only got about 20 volts across each of the capacitors, which kind of makes sense because they've almost completely neutralized each other. If they had started with the same amount of charge on each, I'd have a voltage difference of 0 across each capacitor because the charge would completely neutralize itself. But here, because the amount of charge held on each capacitor plate is reduced in magnitude by a lot, you just reduce the potential difference across each plate. Less charge means less potential difference. So again, it's really the charge moving around that's determining a lot of what's actually happening here, and the voltage is not really telling you a whole lot. It's not the intuitive thing. The charge is the intuitive thing to keep track of here, at least for me. So that's the way I think about this problem. I think it illustrates a lot of the physics of what's actually happening in capacitors, because you have to think about the way that charge moves around when you connect different parts of these capacitors to each other. So I hope that made sense. I hope it was illustrative of some of the conceptual ways to think about these problems, and then some of the problem solving you might do with them. And I will see you all soon. Okay, bye.